ready to build some cool stuff. So I'm going to give you a little while to support the water because I will get to actually jump this more than I should have. In the time I've been here already over the past few days, I'm going to run you through a bit of a high-level introduction to the Radix engine scripto. Much better, yeah. I'll just take you through a high-level kind of overview of what the main tools are that you're going to be using, what the main concepts are, why you need to think a little bit differently when building on Radix as you would on, say, Solidity. It's a slightly different mindset, but the benefit of that difference in the way that you build gives you kind of security, ease of build. It's more intuitive once you get a feel for it. It's more secure and it's more efficient to build. You can build faster, you're not having to put together lots of boilerplate code and think about, okay, when I'm building this contract, I need to import this. It's a more streamlined building experience. So I'm not going to go too deep because while you guys are hacking away over there, there's a bunch of guys from the Radix community who are scripto and Radix engine experts. I'm just going to give you a bit of an overview. So the biggest difference between what we have in scripto and what you're probably used to in other smart contract languages is that we have an asset-oriented model. And what that means is that when you think about tokens that you're moving, when you're making a payment, making a transfer, the development language is very much geared towards how an asset behaves, right? The physical interactions that you would have with a real world asset. So like if you've got $10 in your pocket and you take that out and you pay with it, that's an asset-oriented interaction, right? You can do kind of your traditional smart contract full-term logic, but beneath all of that is a set of asset-oriented constraints that make it very easy for you to build and not have to worry about what the token is doing. Because the token, the way that the tokens move around, the way that the system is secured is at the native level. So when we think about generic smart contracts, it's kind of what you think about, right? You've got some computation that happens and you've got some smart contracts that are deployed on the network. And then these smart contracts can send messages to each other. So something happens here and you want to interact with that smart contract by compose transactions of different actions. And you send messages around. And at first glance that seems pretty good. Right? So, okay, yeah, that makes sense. It's sending messages between smart contracts. I can call this from here and I can call that from there and it all happens. And so when you think about something like Uniswap, this is generally what you think is going on in the contract, right? You send some tokens, you call the trade function in Uniswap. Logic happens here, calculates what is the pool, what is the price, how much the slip is going to be. It puts your tokens in the A token pool, and then it takes some tokens from the B token pool and gives them to you, right? That's what we think is going on. It's quite intuitive to think about it that way. Well, that's really what's going on underneath the hood with a Uniswap. And I'm not going to go through all of this because it gets very complicated, but essentially you've got all these messages. So if you want to trade, then you're authorizing some ERC20 contracts to be able to move your tokens on behalf of Uniswap. You call the trade, there's a bunch of stuff here that happens. Transfer, there's enough balance, update the reserves, LP token balances, and all these messages are going back and forth. And that ends up being quite complex, right? There's a lot of things that you've got to keep track of here. If you're building a Uniswap contract, you've got to check balancing, you've got to make sure that you don't do any re-entrancy, all these messages, you have to manage them as a developer when you're building these applications, right? Because really, as a developer, what you're doing is that you're trying to make sure that the result of all these messages results in an asset-oriented execution, right? This asset cannot be used here twice, or if I send and transfer the asset there. I want to make sure that it's now there and it's not stuck over here because something didn't happen in the loop. So essentially, as a builder, when you're building on something like Solidity, what you're trying to do is make it behave as if it is asset oriented, but you're having to do it in a Turing complete way without any finite state machines, guardrails around constraints to make sure that you can't do certain things with the asset that you might want to do. And because those actions aren't baked into the protocol, when you're developing on, say, Solidity, you end up having to reinvent the wheel a lot because it's not native to the protocol. And you're trying to build these applications to mimic what an asset-oriented model actually does, naturally. So, the Radix engine, it's a bit simpler because we have all of this plumbing and scaffolding underneath that takes care of most of the complexity around moving assets around, making sure that they're not re-entrancy, making sure they're where they should be, making sure that you can't overspend, making sure that there are these constraints that are withheld within the system. So a lot of the complexity that you would have to build on Solidity for Uniswap just naturally goes away because of the development model that we're working with. So here, these are essentially your smart contracts in the Radix world, which we call components, and we have these things called resources. Right? So you have a resource, which most of the time is a token, right? And that token has some rules assigned to it. So there's a native set of rules that resource has to always adhere to if it's a token. So you can mint it, you can burn it, you can transfer it, etc. And those resources are managed by the finite state machine. So I'm sure you know the finite state machine as in developers. So there's only a certain set of states that this resource can be in at any time, and the transition from one state to another is guarded. So you can't mistakenly put it into a state that it can't be in because this finite state machine, you're building against prevention from doing those kind of mistakes. And then we still have messages, but most of the time what we're actually doing is sending resources. Right? We're moving resources rather than messages because the movement of a resource from one place to another is a message anyway. Right? So we still have some explicit messages that go between contracts, but most of the time we're moving and managing resources within this finite state machine, this asset-oriented model. So what is a resource? So resources are native implementations of assets. So this is what I said. So the protocol understands what an asset can and can't do. It's baked into the protocol that an asset can't be in two places at the same time. That somebody must either own that asset or that asset is in flight. There's very specific, very explicit rules around what resources, assets can and can't do and when they can and can't do it. All the resources are implemented through the finite state machine. Right? So that guarantees that when you want to do a certain transition with an asset, you're guaranteed that it either happens or there's some exceptions. There's no surprise about these finite state machine. You want to do a particular thing, it does it or it doesn't do it. And you as a developer will know if it's successful or not. Resources behave like physical objects, right? They give, they take, they put, they move. So when you're manipulating them, the functions that you're using, the functions that you're calling, you can think of them as I am physically moving this object from one place to another. I am giving this object to somebody. I am taking this object from somebody. So when you get into that mindset, it becomes very intuitive because you can think of it very much like I'm giving somebody $10 and they're going to give me a packet of biscuits back, right? There's an interaction, yeah? You get $10, I get some biscuits and hopefully some change, otherwise they're expensive biscuits. And resources can be fungible or non-fungible. If you have fungible or non-fungible assets, you still use the same tools, you still have the same interaction. Because even though it's a non-fungible asset, it still behaves in a physical way. Right? I can give it, I can take it, I can put it here, I can move it there. So even NFTs behave in the same way. even though there's some metadata around them where they're not actually tokens and they're not divisible, but the way that you manage them, the way that you move them is exactly the same as with all the assets. So I'm sure some guys in the audience here thinking about doing some NFT style stuff, so they will be very cool with that too. So we're getting a little bit deeper now into some of the tools, some of the functions that you'll be able to use that exhibit this kind of physical mentality of moving assets around. And all assets live in resource containers. So the two main resource containers that you will be using is a vault and a bucket. Now a vault is where tokens or assets or resources, that's where they're at rest. Nothing's happening with them, they're in a vault, they're not being interacted with right now, they're at rest. If you have assets that you're doing something with, they're in flight and they live temporarily in buckets. So you can think of, okay, I'm going to do some transaction, I'm going to take from this vault, I'm going to put it into a bucket, I'm going to do something else with it maybe, and then at the end of the transaction, those tokens in that bucket are going to get put into maybe a different vault. Right? So in the case of a simple transfer, you would take from one vault, put it in a bucket, and then from that bucket you would put it into the recipient's vault. Transaction finished, all the buckets are empty, you can't have hanging buckets at the end of the transaction. Either you burn or you put what's left over in buckets into vaults, which is another hard constraint of the system so that you don't accidentally forget to empty that bucket and then there's some tokens just lost in the ether circle. There's very distinct rules about how you manage buckets, how you manage vaults. Those rules are simple, they're intuitive, and it means that you just don't make mistakes like that. A million tokens lying around, you can't access anymore because you forgot to put them in the vault. You should be doing that kind of stuff. So vaults are permanent, buckets are temporary. I'm just going to make that to one note here as well. So, yeah, I think we'll get to this a little bit later on in the slide as well, but I just want to, you can have multiple buckets in your transaction, right? So I can take from one vault, put it in one bucket, I can take from another vault, put it in another bucket, I can call another component, smart contract with one of the buckets, I can then pull another one with another. So this concept of buckets and vaults gives you a lot of power in terms of composing transactions, but you'll also very easily be able to monitor the workflow of the tokens that you're moving around. And you can think of, going back to the physical mentality of thinking about this stuff, you're taking from the vault, right? You're putting into the vault. There's kind of physical actions. If you think about the way that you're managing the assets in a physical sense, it'll be even more intuitive too. I can put stuff in a bucket, I can then move the bucket. It's quite hard to move a vault, right? You need a forklift truck or something to move a bucket. In a bucket, you can move a bucket around. So just think of it in that physical way when you're dealing with tokens, and that should make it a lot more intuitive. So when you create a new token, it's a resource, there are some properties that you can define with tokens. So all resources have metadata, there's metadata in there. It's an NFT, then you might have a link to the picture that it represents, or some artwork, or whatever that NFT represents. But in this case, we're making a token, so we can say, okay, look, this is a fungible type, give it its name, its symbol, damn coin, or whatever you want to call it, or jetty coin. You can say there's some rules, right? So there's a fixed supply of one of the tokens. And this information is contained in the resource manager, which represents that coin. Then you can mix some of those coins into a bucket, and then that bucket gets emptied out into a box and into the token. So quite simple. I'm starting to, you guys are getting ahead of me a little bit, hopefully, in terms of what I'm explaining here, and on these slides, just going to piece it together, which will be the perfect outcome. You don't need me all the slides anymore, we'll see how you need to do it. So, you can also define the rules for a particular resource. It's quite a diverse set of rules. So you can say they can be minted, right? Because you might not want anybody else to be able to mint the token. If the token is strictly fixed supply, then maybe you don't want that rule enabled, so nobody can have a mint any more of those tokens, like even the owner is going to find that. You can say, I don't want this token to be burnable, because a developer that's doing some application, maybe they want to be able to burn token. If they don't empty all the buckets, they just burn what's left in the bucket because that's part of their application logic. But you could say, well, this token you can't burn, or only certain people can burn. You can also set rules around withdrawal, deposit, who can withdraw, who can deposit, depending on what life cycle the application may be in, depending on what you need the application to do at any moment in time. You can set and define these rules as you need your token to behave that aligns with your use case. Recall, freeze. People get scared about that one, right? But imagine, a backed US dollar stablecoin that you were to build, and it became very popular, like maybe Circle or USD, Tether. There may be some legal requirements, so you don't get into trouble with the SEC and code, that you need to freeze certain individuals' accounts, right? Not because you want to, but because legally you have to, right? You can say there's only certain individuals that can call the freeze function. So if your application needed to be able to do that stuff, this isn't a freeze where everybody's tokens get frozen. All of these recall, freeze functionality, they are off by default. So if you don't need that functionality, they're off by default. If you do need it for some reason, legal compliance, whatever, then you can enable it. But all these rules you can define, you can set them, you can change the rules, who can burn, who can mint, who can withdraw, and you can put them together in a ruling way. So you can say, okay, to burn this token it needs to be this key with this key, and these are the individuals, so you can like multi-signals in this case too. Okay, so a couple of little examples of workflow. So minting is the state transition from not existing to existing. And so if you have your mint rule defined appropriately, you can call that resource to mint some new tokens. And so what happens here is upon that call, the rule is checked. Okay, can this token be minted? Yes, no. And can the caller, which is calling the mint function, really have the authority to mint these tokens? And if all that checks out, yes. However many tokens you requested to mint ends up in a bucket. When you're finished with your transaction, either those tokens in that bucket go into a vault, or you burn them again. That's what it is. Burning is essentially the reverse, right? So you have some tokens that are in a bucket, and you want to burn them, so you call the burn. Checks the rules. Is this token burnable? Who is calling the burn function? Are they allowed to? You can see here there's some various combinations of the different rules, deny all. So for example, if token is forever fixed supply, when the minter updates and burner updates it, they should all be deny all. So you can't burn them, you can't mint anymore. Similarly, you can make a token with only decreasing supply. So you can't mint anymore, but you can burn. Flexible around the rules on token. Depositing, that's the state transition from going from a bucket to a vault, right? And there may be certain rules where you actually don't want tokens to be deposited. You might say, okay, because you're running an airdrop campaign or you're doing some other business logic where you only want to deposit to possible to certain accounts. You might say, okay, this isn't a freely tradable asset anymore. These tokens can only be deposited to vaults which have been pre-approved. And you can do the same with the withdraw function as well. You can say, okay, the application flow that I need means that only certain people can withdraw from the function. I'm getting ahead of myself already. So essentially the point here is that you have these rules that are simple in their their own definitions. You can combine them, you can set various parameters around them, so you can have very complex, very exotic rules around what the token of resources can do, where they can go to, how they can be traded, and what rules can they be traded. But you don't have to worry about any of that stuff as a developer. You don't have to build the logic that guarantees those rules are met. Because these are native to the protocol. You just set the rules and the system takes care of it for you. You don't have to build any of this stuff. You can have very complex and interesting token life cycles in transactions. A few more behaviors like recalling allows you to make seeds with tokens from outside the component. So I can remove from a vault. Freezing allows you to take in a vault to put in a state where withdrawal or deposit will fail. This is like the example I was giving. If you have a stable coin to allow some regulation or something. Combinations of rules that you create just about any kind of token behavior you can think of. And that's possible because the constraints are very well defined, the rules are very well defined, and most of the hard work is taken care of by the protocol for you. And you have these guarantees about what will and what will not happen. Another nice thing is, because resources are native to the system, there's no surprise when it comes to what can this token do. Right? So, I as a user, I can look at a token and I can see the behaviors that it has, because these behaviors are based upon the rules that have been set and the parameters of those rules. So, I might be wary that this particular token may suddenly get burnt. So it's a rug pull, right? Or something like that. But I can, because I'm native, I don't have to go and crawl through a smart contract to try and figure out, is this token legitimate? Is it suddenly going to get rolled? Or is the supply going to get burned when the developers have said that we're never burning any, but there's a burn function in there? Why is that there? You can see all of this stuff just here in Explorer, in your wallet. You can see what rules, what behaviors are assigned to particular assets. Oh, I'm not sure what's happened with that slide. Okay, I think. Okay, that slide clearly. Somebody's put 3 slides on top of one thing. So what this is just a little snippet of code that is showing you a new fungible token, what the role is, divisibility, none, NFT I guess, what metadata you can have, special token, the symbol, the mint goals. So these are kind of the rules that we were just talking about, but I think there should be a few slides here that have been put on top of each other that would walk you through this. So can't really do that with this one. I think this is essentially making a new fungible token and setting some of the parameters. The main, the token symbol, what roles there are, what the initial supply is that it's minted with, who can access, who can change minted roles, that kind of thing. Slides. So that's quite a lot to start with. So I'm going to get a sip of water and then I'll take some questions from you guys at the moment.
Hi. What kind of submission are you expecting from us? Like a GitHub repo or a video demo? What do you need for the event?
I mean, yeah, GitHub repo would be cool. That'd be nice and easy. A video demonstration as well, just in case we have any issue, running a demo from the GitHub repo. Yeah, if you can have a GitHub repo or some form of repo for the code, and then yeah, either a video recording of the demonstration.
Yeah.
Yeah, they should be, yeah. We'll deal with that when we get over there. Any other questions at this stage? Yeah.
Hello. You said that when you create a transaction, goes to the bucket, and then if there's anything left, where does it go, or where do you code that part where it falls back in excess or whatever is remaining?
Sure. So let's say that you've taken a quantity of tokens out of the vault, right? And then you call the swap pool, and you expect a certain amount of tokens to come back from the swap pool, but actually you get more than you expect, right? Obviously, you can either just put all of those tokens into a vault and done really well because the slippage was low, maybe in your application logic, you need to, you don't want all those tokens, right? So I got 120 back, I only wanted 100, either I can just send the additional 20 back to another vault, or if it's part of the application logic, right, I can burn them. Right? So at the end of the transaction, whatever you've been doing, whatever's in the buckets, either all the buckets have to be empty, or you have to explicitly say whatever's left in buckets, burn it.
I have a couple of more questions. I think you mentioned it, but I'm not sure if I got it correctly. After the token is created, you can still update the rules?
Yes, you can. That will be visible in the application, the wallet, it will be visible kind of in the Explorer, so you can't secretly change a rule and hope nobody notices, right? It's very transparent.
Okay, the last question is the burning. When I create, not the freezing, when I create the token, I have to set up an admin for the freezing or...
Yes. Well, you can set up, there'll be multiple admins, right? You need to define who those people are that can call the freeze function.
Okay, so if the freeze function is enabled, I have to set up on one or multiple admins.
However many you want.
Thank you very much.
Any more? Okay, all make sense? Give me a hell yeah. Great. That means I'm doing my job well. Okay, now next section. I told you we'd be here for a while. So maybe we better take a bathroom break or something. I don't know. So next is components and blueprints, right? With Solidity, you would have smart contracts. And you can think of components here as smart contracts, but that's probably the wrong way of thinking about what blueprints and components really are. Right? They're both simpler, but also more powerful concepts. So with a component, you have what's called a blueprint, which that component is instantiated from. And the component may have some resources, like a vault with some coins in, or some metadata, and some methods can be called, right? But how do you get this component in the first place? Well, that's a great question. So, the component is instantiated from a blueprint. Now, you can think of a blueprint as a class definition file, right? So, for object-oriented language, C++, you have class, Java, you have classes, right? So the blueprint is essentially a class definition, but you don't call the class definition, right? You instantiate that class by the constructor, and then you interact with that class. This is the same kind of model, right? You have a blueprint, which is a class definition file, and then your component is akin to instantiations of that class. Now, blueprints are exactly as they sound. They're a blueprint. They hold the logic that you will be executing if you call that component, but it doesn't have actual resources. It may have resource definitions that will be created upon instantiation, but it doesn't actually hold any resources. It's just a template. So you call the constructor method on the blueprints, which is really a package. A package may contain multiple blueprints. So if you're doing quite a complex application, you want to have some structure to your application and not just have everything in one single blueprint. It's like a brain blueprint. And you can have packages, package blueprints together, call a constructor within a particular blueprint, and you'll get a component instantiation. So your constructor that you call the blueprint can actually have quite a complicated instantiation procedure, right? So instead of it just creating a component, maybe calling the new function on the blueprint, it creates a bunch of components that you need and creates some new tokens and mints some tokens and puts them into buckets. So you may need all of this for your particular application, and you can instantiate all of these objects that you need from a single blueprint call. Oracle component, different tokens. And upon calling the new function, you can also define some of the rules and things and the constraints around tokens and the resources that your application is going to use. Yeah, the battery's on. So, just to sum up, the blueprint is a template, a structure, holds all of the definitions of the logic with the any resources. A component is an instantiation of the blueprint, and that may have resources. You can call it, you can interact with it, it has some state. And a package is a collection of blueprints that you can compile, deploy to the network. And you can instantiate blueprints from the package. It's okay. So obviously you can have multiple instantiations of the same blueprint, right? So there may be a Uniswap style pool blueprint that somebody has made, and I want to have, I want to make a pool, but I don't want to build the blueprint for that. That's okay because somebody's already built one. So I can just instantiate their pool blueprint if I've done my due diligence and been through the blueprint code to make sure that it's good. Anybody can instantiate any blueprints. And that's interesting because we have within the Radix network developer royalties. So if somebody is instantiating a blueprint many times, then you can get some revenue from the fees that are collected from interaction with that blueprint. Okay, now we move on to everybody good with the packages, blueprints? It's fairly simple, right? Okay, so accounts are very different on Radix as well, especially when you compare to Ethereum, right? So an account on Ethereum is, it's kind of Alice's address, and then you've got these ERC20 or variations of ERC20 contracts that keep the balances of whatever tokens Alice's address holds, right? So it's not really an account as such because the information for that account is distributed around all these different other contracts which can keep a balance of what my holding of that token is, but there is no real single place where I can just go and grab everything that address that account represents. So it's kind of like quite messy, right? You're going to make a lot of calls everywhere. You're going to interact with a lot of smart contracts if you want a full breakdown of all the tokens that are held by Alice. But on Radix, an account is actually a component, essentially. Right? So an account is instantiated from a native account blueprint, and then that account is then a component. And components can hold state, components can hold vaults, can hold resources, right? And there's some defined interactions you can do with accounts, essentially withdraw and deposit. But it's all in one place, right? I don't have to jump around a bunch of different contracts to figure out, okay, what is my total balance across all tokens that I hold? I can just look at Alice's account components, so much simpler in terms of the interactions with. And then when I want to, say Alice wants to spend some of the 50 USD, then I just call the withdrawal. some of Alice's USD will go from a vault into a bucket, and then I can use that bucket, pass it to other smart contract pools, whatever it is. Okay, yeah, so here's a little bit of a workflow, right? So simple transaction, Alice is going to send some subs to Bob, and so the transaction calls that happen. Call Alice, withdraw 5 SERP. If there is some proof of authority that Alice can do that, like a signature, sign the transaction, then 5 SERPs will get placed into a bucket. And the next call, 5 buckets get deposited to Bob. Bob might have some rules here that say, I don't want SERP tokens, so that call would fail because Bob has defined it. I don't want SERPs, they're shit, but I don't want them. Anybody ever tries to send me some SERPs, just kill the transaction. And that's essentially all that you have to do to call a simple transaction. If you want to do something a little bit more exotic, like a swap, again, the workflow is nice and simple, it's intuitive from a developer point of view. So Alice's account, I want to swap in Radix swap, which is like a Uniswap, DEX, let's say. I want to swap some tokens A to token B, right? So I call the Alice account with a withdrawal of 100 tokens. Alice has signed the transaction, so we know that it's really Alice. 100 tokens come out into a bucket. We then call the Radix swap trade function with the 100 tokens in a bucket. Then we get however many token B comes out, current price. And then however many token Bs we've got, if we're happy with that, then we call the deposit function on Alice's account, and we're all done. And that's it. Just 3 nice, easy lines in the transaction manifest, which we'll get to in a minute. No fancy, complicated stuff. That's essentially the workflow. I think there's been some issues with some of these slides, but there's definitely a couple missing maybe here as well. We'll go back one more. Yeah, one more, yeah. And again, one more. Okay. There's another piece here. There should have been another slide, I'm not sure what's happened to it. Essentially what you can do as well, when you're doing these kind of calls, you can essentially set guarantees, right? So in the transaction manifest, you can say, if I don't get a certain amount of tokens back that I was expecting from the Radix swap, right? So if I was expecting 150, but I only get back 120, then just terminate the transaction. Don't change any states, just abort the transaction, everything goes back to my account. So you can set these guarantees both from a user perspective, if you're savvy enough to set them, or from a developer perspective, when you're building an application, you can say, okay, if the outcome of what my application flow is doing doesn't meet what I expect as a developer, I can also just abort this transaction. I can put these very strict, definite guardrails around the transaction, the state transition within that transaction, where resources are going, what resources are going back. You can be very explicit around it. This doesn't happen the way it should, but so you can have some of those kind of asserts, basically, right? It's kind of like if I was flying to Barcelona and from the UK, I want to get some euros. So I go to the currency exchange, I take £100 from my pocket and I say to the teller, hey, I want some euros. And the teller takes them and then he gives me back 20 euros and they say, whoa, hey, that's a bad deal. No, deal's off, right? Give me my 100 back. Hopefully it gives you back in some principles. But you can kind of think of it again in that way, right? I'm taking something, I'm giving something to somebody, I get something back. If what I get back isn't what I expect, deal's off, transaction. So yeah, I kind of touched on this already earlier on. So non-fungibles work in exactly the same way, except obviously some of the parameters of non-fungible are a bit different, right? They're non-divisible, they have some additional metadata, etc. But hopefully at this point you can visualize that, I see how non-fungibles just work in the same way, right? I I take it from somewhere, I put it in a bucket, I do some actions on the tokens within that bucket, and at the end, I either burn what's left or I move them into the destination. Same for all of the tokens. Oh, yeah, another queue, just to make sure everybody's.
Do you support any methods to make cross-chain swap?
So there's no native methods that allow cross-chain swaps at the moment. There are protocols within the Radix ecosystem that can do cross-chain swaps.
So I have to write a bridge.
Yeah, or you can use Maya protocol, for example. Like they support methods you can go through ForSwap. There's a couple of Radix ecosystem projects that support bridging as well, like Mr. Solomon.
Okay, thank you.
Is there a specific use case you're thinking of?
No, just check if I can, for example, swap Ethereum, that is very common, to Radix coins and use Radix coins for other transactions.
Yeah. So there are those they exist within the ecosystem. Right? Maya protocol by ForSwap, you can trace from Ethereum or Bitcoin or USDT to XRP. There is no kind of call you can make in your transaction to just magically do that.
Okay, at least are there any methods to use like stablecoins inside if you want for swapping the coins?
Yeah, so if you bridged from USDC, for example, right, then they just behave in the same way as any other asset. So it's a representation of USDC that you bridged over. You can go in a vault, you can be in a bucket, you can interact with it in the same way as you would a native Radix token or an all of the same take, port, bucket, vault, those things to apply.
Better, thanks.
Hello. You said that the components have what's the name of the card if I want to use a component that other person created, then we get some.
Yeah. So if you the blueprints. Right?
The blueprints, yeah. I was wondering if the blueprints are not then open source.
So the blueprints you can inspect. They also get open source for GitHub repos and stuff, right? So if you wanted to use a particular blueprint and you knew who had made it and they were in a GitHub repo, then you could audit it, right?
Okay, that was my question.
It's like, okay, yeah, this is legitimate, then I'll use that blueprint, right? Obviously, if you're a serious developer and you're thinking, okay, I'm going to make these blueprints and I'm going to earn some revenue from the use of those blueprints, then that would be the process that you follow. Right? I want people to be able to audit what blueprints do because there's potential revenue generation as a developer.
Okay, thank you.
So hopefully over time there'll be a nice library of different blueprints that have been made, right? And so as developers, ultimately the nice place to be would be no one's really writing many blueprints because there's such a nice collection of them already in the ecosystem. People just piece those together for most of what they want to do, and then just put some glue in the middle that defines the very specific application logic that they might need for their use case.
Perfect, thank you.
Any final?
It's not so much about what the last talked about, but it's a question around the ethos, the value of making it simple for developers to develop. My question is around particularly about true randomness, because I imagine that at some point you thought this is a problem that we could solve if we're not 100% decentralized. We could solve that for developers. Have you ever thought about that?
Yeah, like true randomness is difficult, right? So I don't believe there's anything in the stack right now that will give you anything like a true random. So your best is going to be pseudo random, seeded by somewhere. Right? So the best you can do is ensure that you have a good quality seed. If you're going to do pseudo random. True random doesn't really exist, I guess.
Thank you.
Okay, any more? Shall we get to the last bit? We're nearly there, guys, don't worry. It's coffee time soon.
So, are there any post-hackathon grants available for projects or anything?
Yeah, we got a grants program. I think that's about $10 million at the moment of grants that you can apply for. And there's various tiers as well, depending on what you're going to do, what the scope is of the project and stuff. So yeah, there is a grant program. So if you build something really cool here today, and it's like, you know what, I want to take this a bit further, then yeah, do it. The grants are open for application. You guys.
Thanks.
Yeah, I just wanted to ask if you guys have any kind of BLS implementation right now or it's
We do have a BLS implementation because part of the Babylon consensus is BLS for signature application and schemes. So
is there anything to do with you guys through BLS?
we could, but I don't believe that's implemented in the Good. Okay, let's get to the last one. We're all tired. We're all very eager to go and build cool things. I'm sure. The next one. Okay, so this bit's quite short actually. So the authorization model we're using Radix is also a bit different, again, for purposes of security, for purposes of ease of use. But it is a little bit abstract because the kind of things that you can do with the authorization model, the abstractness is power rather than hindrance. So if you really want to understand learning the authorization model, it's probably better to go through documentation, which will explain it a lot better than I can on this stage in 10 minutes. But just to give you a bit of a very high level overview of what the authorization model does and what it looks like. Just go through a couple of slides and plant that seed to think through the docs. So, whatever you're trying to do, you're going to need some kind of authorization, right? Whether that's a signature, whether it's some other kind of proof. And the rules of how you interact with a particular token, like the make function, or a restricted withdrawal, where you have to be a certain party that can interact with it. The system requires proof, right? Are you authorized to be able to do this activity that you're trying to do? And proofs, show that something is true. Key component address, so the component calling another component could be the authority. Right? This component is allowed to do these actions within this component, and nobody else is allowed to do anything in this component other than that component B. So the components themselves can be the authority. You can have resources, right? Called badges. So I have a badge which says I'm allowed to do this interaction because I'm possessing of this badge. If I didn't have the badge, then I can't do this functionality because I need that badge to be able to satisfy the rules around minting, building, or whatever it is. Right? And the badges don't really move or anything. Again, from a kind of physical point of view, you're showing your badge, right? It's like, here's my badge to say that I have authority to do this action. And then once you show the badge, and you can take something and you can put something back. So badges make up, they allow you to have really quite exotic and interesting authorization flows. So you can have, so you could say, okay, in these rules, there should be, if I want to access this functionality, then there needs to be a supervisor, an admin, and a superadmin. Like these might have a supervisor badge, an admin badge, a superadmin badge. And to do this functionality, we need all of those three guys to show their badge so that they can, whatever the rule is required for, like mint, boom, ritual, or whatever. Or you can say, if we don't have that, then if we have if the founder shows their badge and 8 of the shareholders show their badge in this transaction, then we can do that action. So you can have very explicit, very flexible rule cases around who is authorized to do this, who is authorized to do that, and you can have combinations of each. So yeah, this is a deep topic. It definitely is, right? There is a rabbit hole here that you can go down, which will be very fulfilling, but it can take more time if you want to stick. So if you want to understand the auth model, I would suggest going to these 2 locations, the auth docs, and there's some examples as well on how you use auth. But in the simplest scenario, it's essentially a signature. I've signed a transaction, and that signature in the transaction means that I can move tokens from Alice to Bob. But in your components, you may have more complex requirements. It may be badges, combinations of permissions, and all those kind of things. So it very much depends on what it is that you want to do, how you want to do it, and there's so many permutations of things you can do. It would take too long. It's a lot of mistakes. So I think that's yes, we made it there. Any final thoughts, questions? No? Okay, everybody's an expert now, so. Alright guys, so I know you're all itching to get started, so there are a number of people from Radix can help you with questions, get you started, put you to the right places to get going, help you set up tool chains, all those kind of things. Unfortunately, I'm going to be bouncing quite a lot while I'm here, but I will pop in and see how you're doing every now and then. But these guys, these are our legends for the day. Thank you all for coming, and I hope you find Scripto as interesting and developer friendly as we think it is, and hopefully you get hooked and you build some cool stuff on Radix and stick around, and we'll see some really cool applications in the future. But on that note, have fun, build some cool shit, and get cracking.